So let's go ahead now and we'll look at the simulation of our depletion NMOS device. So in this device the threshold voltage is -4 volts. So let's go and set that up and we'll go have a look at it. So we'll put this to -4 volts. You can see here again we're back to the N type and the N type. So let's go ahead and we'll leave the beta values exactly as they are. And we'll get into the gate source and drain voltages. So just to get a comprehension of this device, you can see here that we've just left it as it was in the previous example. The gate voltage is at 5 volts, the source is at 0 volts and the drain is at 3 volts. But you can see here that the device is on and it's carrying a lot of current, and you can see the current here, it's way up here. So in this instance the device is on whenever the gate source, the gate voltage is at 5 volts, but it's also on whenever the gate voltage is all the way down at 0 volts. So if I go to 0 volts here, you can see that the device is still on and it's still drawing current. So this is the IDS versus the VDS curve here, and you can see here that at this point here it's actually in the linear region and it's drawing this current here. So we can say there then that this device in effect is normally on. So in order to turn the device off, you can see here we're going to have to get rid of this inversion layer. To get rid of the inversion layer here, we're going to have to make the gate source voltage negative. In fact, we're going to have to make the gate source voltage less than -4, which is the threshold voltage. You can see as we do that here, we're going to make the inversion layer smaller and smaller, so it's narrower and narrower, until eventually we get the gate voltage goes down to -4. So at -4 volts here, we can see that the device now is turned off. So to turn this device off, the gate voltage would have to drop all the way down to -4 volts. So we can see here that this device would in effect be normally sitting on at 0 volts. Now this device is called a depletion device because in the area below the oxide layer, that is the channel here, it's depleted of the charge carrier. So the charge carriers in this case is the P-type material, which are holes. So in the previous device it was an enhancement device, meaning that in effect you could call this area, if you like, you could call it P+, that is, it's highly P-type, meaning that there's a lot of holes in this region. But now we're working with an enhancement device, a depletion device. We're actually depleted of those holes. So that's why it's called a depletion device. So it means that if we're depleted of those holes, if the source and the drain voltage, say for example, were the same voltage, so let's put them at the same voltage. Let's make them both at 3 volts. So make both of them 3 volts. You can see here that the gate voltage sits at 0 volts. So at 0 volts, there's still a channel that actually exists below this region at 0 volts. So the actual graphical representation of this depletion NMOS will have a little line from here to here. It's not shown in here, but I will draw it in just in a second. So that's why we've got this little line drawn in here, because at 0 volts this device is normally on, and that represents the little channel that exists along here at 0 volts. Again, we could change the drain and the source terminals. So if we were to make the drain terminal actually less than the source here, then the drain and the source terminals in effect would change. So if I drop that down here, you would see that we would now have the current would now be flowing in the opposite direction. So the current would be flowing from the source to the drain, so in this direction here. So the majority carriers are going to be electrons travelling from a source to a drain. And you can see here that we've got that partially modelled in the diagram here, because you can see here that the current is actually now going to be a negative value, and the drain source voltage is going to be negative as well, because the drain and the source have been switched round. But we're not going to use the device like that. We're going to keep these represented as they actually are. That is, the drain voltage is going to be greater than the source voltage. just to avoid any confusion. So we will be running it in effect in this region here. So I suggest you open up the simulation tool and give it a little go and mess about with it and ensure that you understand the current flows and what direction the current is flowing in and so on and so forth. Now don't worry too much, because I know we're going to go through 4 devices and it can get quite confusing about between one device and another, but whenever we go on and use these devices in the digital circuit design, we'll only be using 3 of them. In fact, we'll only be using ever 2 at a time, and it'll become obvious as we start building up the circuits and the different technologies that we're going to be using. So for example, we're going to have a quick look at the PMOS technology, but that isn't so prevalent now, so we will be really covering the NMOS design, which was again our design in older transistors, and we'll also be looking at the CMOS design, and most of the course in digital design will be in the CMOS logic. So there's only really the 2 logics we're going to be looking at, the NMOS and the CMOS, and all the other details here that you see and you have learned here won't actually really be necessary within the digital design course, but it's useful to understand them, and it's actually really necessary to understand them if you ever go ahead and you do analog design, which we'll do a little bit in this course near the end. So don't worry too much if you're not picking up all of this. So thank you for listening. I'll get you in the next video. Goodbye.